Hello everyone, good morning or good afternoon. Good morning and good afternoon to all of you who are listening to us via the streaming platform. My name is Alaric Montenon and I will just speak about the topic of solar concentration system for the built environment, and I will end with the Cyprus Institute experience. According to EAC, the Electricity Authority of Cyprus, commercial and domestic users represented more than 75% of the electricity sales in 2016. And the energy mix was based on 9.3% on renewables, while the target is 13% for 2020. Let's have a look on in this special year 2016 on the solar energy. So main use was based on photovoltaics and solar thermal collectors. So 146 gigawatt hour produced for a bit more than 100 megawatt electric installed. And solar water heating represents more than almost 400 kilowatts thermal installed per 1,000 inhabitants, and this represents the third capacity installed in the world per inhabitant. So let's have a look now about a bit more about these domestic and commercial users. The building and energy final demand will increase. It's not a new announcement I'm doing here, and we saw that also through the presentation of Fabio. And at the scale of Cyprus, let's have a look on the forecast from 2013 up to 2015 based on a GRC report. The thermal needs, meaning cooling demand, heating demand, and hot water, are going to increase, and especially for the cooling demand. So it will be more than double with an increase of 112%, and for the commercial buildings by 28%. The building heating demand also will increase, but it's more moderated compared to the cooling demand. So the increase will be for both types of buildings by 15%. Water heating will evolve quite moderately compared to the heating and the cooling demand. So first, heating and cooling needs for buildings are supported by mainly so far by the electricity grid, as we saw before through the presentations. And this electricity grid relies mainly on fossil fuels. Hot water demand, as we see, represents a minor share of both building types demand. So, in other words, cooling and heating are responsible of the emission of greenhouse effect gases. So, cooling means heating. Why? Let's say that it's hot outside. What are we going to do? We are going to turn on the AC unit. This AC is powered by what? By the distribution system transmitted from the production sites. And in fine, what's happening is that the more we need to cool, we are heating more locally. That's one of the indirect effects. So is it a fatality? I will try to show you that. No, obviously, in the next slides. So this map, you have seen it before. So this is the map for direct solar radiation in Europe and part of the Mediterranean area. This is the same image processed before, where the DNI is more than 1750 kilowatt hour per square meter per year. And you see, now let's have a look on Cyprus. You saw this map as well. So let's emphasize a bit on this map compared to the energy consumption of Cyprus. So the DNI average on the level of the island is 2072 kilowatt hour per square meter, and it's a really good figure to think about CSP, as you understood from the previous presentations. On the island, this represents more than 19,000 terawatt hour of direct normal radiation. Now let's have a look to the primary energy consumption in the Republic of Cyprus in 2016. it's 25.5 terawatt hour. You see the difference. And to even emphasize on it, EU20, the primary energy consumption in 2016 again was almost 18,000 terawatt hour. So let's consider now a system that will have 10% of efficiency in the conversion of the DNI. The land required to power all the energy needed in 2016 for Cyprus, we will need only a square of 11 kilometers by 11 kilometers. So we saw that cooling and heating represented a huge demand of basically the energy demand of the island, and especially for buildings. So the Cyprus Institute, all together with other partners from the STS Med program, and Fabio, who is represented ARCA here, has been mentioning this program before. So we tried with a Fresnel collector, basically, to integrate heating and cooling on this building where we are standing now. The DNI registered with our parameter here installed on the top of the roof was almost 2,000 kilowatt hour per square meter. The facility is in operation since 2016, and it covers up to 34% of the cooling and heating needs of this building here. The collector itself has a thermal peak capacity of 85 kilowatts. It has a north-south orientation, 288 mirrors driven by 72 DC motors, 9 tons, and this represents less than 25 kilograms per square meter. So even on an old building, we could integrate easily this facility, okay, with the help of some beams that you can see here. It works with thermal oil up to 180 degrees, but this kind of collector, even small like this, can operate to much higher temperature, but for safety concerns, we limited ourselves to this temperature. The receiver is 32 meters long with 8 absorber tubes in series. The storage medium that we're using is very simple. It's simply water. That we can heat up to 146 degrees. This represents 2 hours of storage during the summer for cooling and 4 hours of heating during the winter. This buffer here is simply a buffer of oil with a simple heaters wrapped around. So in the morning we avoid the oil to be thick for pumping purpose, and this is simply an expansion tank. Cooling is performed with an absorption chiller, single effect COP of 0.7. It means that it requires 50 kilowatt heat to cool down, to remove 35 kilowatts of heat from the chilled water. During the winter, it's simply bypassed, and from the heat of the Fresnel, we directly go to the heating system of this building here. So this is an absorption chiller. I will not extend on the technology, but just with heat here, instead of a compressor for classical heat pumps, just with this heat input, we basically cool thanks to solar energy. And the electricity that is mainly required is this small pump, which consumes much less than a compressor from a heat pump. The Novel Technology Laboratory has been delivered in 2013 and inaugurated in 2014 April. It also has a north-south orientation, few windows on the south, and you see some of them here. So we avoid to heat up when at the hottest moment of the day. Also, there are some grids, as you have seen, on the western and eastern facades, which avoid also the solar radiation to basically warm up the walls. And also, there are some PVs integrated on the roof, 14 kilowatt peak. There was a proposal from this Fresnel collector that we are not likely to proceed to, but for this type of buildings here in Cyprus with flat roofs, basically for this kind of use, during the weekends, we don't need heating and cooling. And this represents 28% of the time of the year. When the temperatures are mild, or whenever the DNI is not good enough, basically the Fresnel needs to be turned off. There are then the bank holidays, closure weeks, for instance, and also whenever the building is not occupied. Eventually, the thermal process is off 61% of the yearly daytime. And when you look at the high capital cost, you understand that cost is not cost efficient, and even the capacity factor is really low. So what to do with this facility? So we propose to upgrade this collector simply using and benefiting from this single axis system, and just to flip it around and to have PVs on it. So basically we could convert this collector to a photovoltaic collector. And this is also kind of joining all the discussion that we had during these days of conference, that hybridization is a must and is a tendency for CSP to be cost effective. And basically the collector, for this 61% of the time that it's in standby for thermal process, we can enjoy the axis of tracking. And the energy that basically would be produced from that would be even better than a standalone collector on the same area, just because we are also tracking on one axis, and also it's even also collecting part of the diffuse light while the thermal process is engaged. This improves by 2 the capacity factor of the such collector. We are more or less harvesting twice the final energy that we would need, that we would just obtain with a Fresnel collector only for thermal process, and it complies with the global needs of a building, which are thermal needs, heating and cooling, and electricity. Also, this collector was proposed also with batteries. So this is for the future. For instance, if according to the let's say fluctuating price of the electricity, which is not yet the case here in Cyprus, but maybe one day it will happen. We don't know. In that case, we could either go to batteries or go to the thermal process, depending on the parameters. And also it depends on the curtailment strategy that maybe will happen. It's not yet the case in many countries, but if there is a huge PV integration in the mix of the national grid, this may happen. And also with the new let's say legislation regarding nearly zero energy building, this could even improve the energy performance of a building by not only having, let's say, an energy balance on the year base, but maybe on shorter periods. So let's say a bit more qualitative. So at the end, we started with that. And what we could demonstrate with this pilot plant here at the Cyprus Institute is that we could simply cool using this Fresnel integrated with the absorption chiller into the building. Thank you.
Again, one quick question. Manuel? You are... Two questions, okay.
One is why, with the high temperature you can get out of the collector, you could have a double effect system, which would be cost basically the same and would give you much more cooling.
Yeah.
So why don't you? That's one question. Second, yeah. One way to mitigate the problem that you discussed, the fact that 61% of the time why don't you cool the building anyways and store cold in the thermal inertia of the building? So the building will be cooler when you come in next morning, even though it's weekend and no one used the building. So playing with thermal inertia on a building that has thermal inertia, I presume quite a bit, would probably be a very good strategy, and you would still be using your Fresnel in a thermal way.
Yeah, regarding the double effect, that's totally true, and it's even cheaper. It's just that at the time that of the project, I went through this technology because I couldn't identify any available on the market. But it's totally true that now, especially in Italy, in Palermo, they have one, and eventually, yes, it's much better. It was just a matter of time. And regarding the cooling during the weekends, yes, that's totally true. It's just a matter of space and also of capacity, and also to have good insulation, and it's totally feasible, yes. But I don't know then if we're able to, let's say, store, let's say, cold for whole the weekend just to release it then during the week. And I don't know, let's say, if we are able to store 2 days of work and to release it in the week after in an efficient way. I'm not sure of that.
Well, it's a matter of calculating and knowing the building and the thermal inertia of the building. But I'm sure you can do much better, reducing the 60%.
Yeah.
40 or 30.
Yeah, it's likely that having a cold storage, actually the temperature difference with the outside is better than having in that application than having a hot storage. Probably at the early stage it would have been better to have a storage maybe, or at least hybridized between the cold side and yeah.
Okay, Alaric, thank you very much. Diego down there insists of asking one more question.
Only one question. What is the cooling system that you use for the heat pump?
What do you mean?
How you cool the pump, how you extract the heat at medium temperature? You have a refrigeration tower, an air...
Yeah, we have a cooling tower, yes.
A cooling tower, water cooling tower.
Yes, associated to the absorption chiller, yes. Lithium bromide, single effect.